Assalamualaikum and hi everyone. We are Group 4 from the Faculty of Technology, Industry and Manufacturing Engineering. Today, we will present our assignment 2 for Mechanics of Material, which focus on the Hintz Ribeiro Bridge collapse in Portugal. This presentation will discuss the background of the bridge, its structural specification, the cause of failure, and the engineering lesson learned from this disaster. Our presentation is divided into 6 main sections. First, we will introduce the background of the bridge. Next, we will discuss the structural specification. Then, we will explain the failure analysis and mechanics of material analysis. After that, we will highlight the engineering lesson learned from the incident. Finally, we will conclude the key findings from the case study. The Hintz Ribeiro Bridge was located in Entre Rios, Portugal. It was built in 1887 and served the community for approximately 114 years. The bridge connected local communities across the Douro River and consisted of steel truss spans supported by masonry piers. On the 1st of March 2021, the bridge suddenly collapsed, resulting in 89 fatalities. This tragedy became one of the worst bridge disasters in Portugal and is now widely studied in mechanics of material because it demonstrates how foundation failure can lead to the collapse of an entire structure. This slide shows the Hintz Ribeiro Bridge before and after the collapse. The image on the left illustrate the bridge when it was still functioning and supporting transportation across the river. The image on the right show the damaging collapse that occurred in 2001. By comparing this image, we can clearly see the several impact of foundation failure on the stability of a bridge structure. This disaster emphasize the importance of regular inspection, maintenance, and monitoring of bridge foundation to ensure public safety.
Now, I will explain the structure specification of the Hintz Ribeiro Bridge. The Hintz Ribeiro Bridge was located in Entre Rios, Portugal, and was constructed in 1887. It was a steel truss bridge supported by masonry piers made from granite, masonry, and structural steel. The bridge served the community for approximately 114 years and played an important role in regional transportation by connecting nearby municipalities. From an engineering perspective, the bridge demonstrated the durability of steel truss construction and masonry pier support system. However, despite its long service life, the bridge eventually collapsed on 4 March 2001 due to foundation-related problems. The collapse later became a well-known case study in civil and structural engineering because it highlights the importance of foundation stability, inspection, and maintenance. Next, I will discuss the failure mechanism and root cause of the bridge collapse. The main cause of the collapse was foundation score. Score occurs when flowing waters remove soil and sediments from around bridge foundation, reducing their support. Several factors contribute to this problem. First, illegal sand extraction lowers the riverbed level. Second, continuous river currents gradually weakened the pier foundations. In addition, flood conditions accelerated the erosion process. Finally, insufficient inspection and monitoring failed to identify the increasing risk. As a result, one of the center masonry piers lost its foundation supports and became unstable. This instability caused the adjacent bridge spans to fail. leading to progressive collapse of the structure. These incidents demonstrated how environmental factors and inadequate maintenance can significantly affect the safety and stability of bridge structure.
For this slide, I will explain the effect of pier failure on structural behavior. This steel structure is designed to be supported across multiple spans. When a pier fails or loses support, the effective span length increases. As a result, several effects can occur, such as an increase in bending moment, higher internal stress, reduced structural stiffness, excessive deflection, and structural instability. The key concept here is that when one support is removed, the load distribution changes significantly, causing the structure to experience force beyond its original design capacity. For this slide, I will explain the bending moment analysis and maximum stress. The assumptions used in this calculation are a span length of 50 meter and a uniformly distributed load of 20,000 Newton per meter. The formula used to calculate the maximum bending moment is WL square divided by 8. After substituting the values into the equation, the maximum bending moment obtained is 6.25 times 10 to the power of 6 Newton meters. For maximum stress, the formula used is sigma equal my over I, where m represents the bending moment, y is the distance from the neutral axis, and I is the moment of inertia. As the bending moment increases, the stress within the structure also increases. Higher stress reduces the structural safety margin and can contribute to structural failure. In addition, increased bending moment also increases internal stress, which may eventually affect the overall performance and stability of the structure.
Good morning, everyone. So right now I will explain the concept of the yield stress and the relation of the Hintz or Ribeiro bridge collapse. The yield stress is a point where the material begins to undergo permanent deformation after being subjected to stress. For a structure steel, yield stress is an important property because it determines maximum stress the material can withstand before the permanent damage. In this case, investigation found that the steel member did not fail primarily because of the yielding. The bridge structure itself was not the main source of the failure. The collapse was mainly caused by the foundation instability, which weakened the support system of the bridge and eventually led to its failure. In the next slide, I will discuss about the bending curvature of the beam. The bending curvature is a measure of how much the beam bends when the load is applied. As the applied load increases, the amount of bending also increases. Excessive bending curvature can create several structural problems such as crack, deformation, and reduced structural ability. In this issue was not addressed, they can affect the overall safety and performance of the structure. Also, about the remedial measure. To reduce structural problem and improve safety, several remedial measures can be implemented. First, steel plate can be added to the strengthening the beam. Second, damaged beam section should be replaced. And the third, routine maintenance should be carried out to prevent a further deterioration. Finally, regular inspections are important to detect damage early and ensure structure remains safe for use. This measure can help extend the service life of the structure and reduce the risk of the future failure.
Several important lessons can be learned from the Hintz-Ribeiro bridge collapse. Foundation stability and continuous scour monitoring are essential for bridge safety. Aging bridges also require regular inspections and maintenance. After the collapse, stronger inspection programs and better riverbed monitoring were implemented. The key lesson is that a bridge can fail even if the structure remains strong when its foundation is weakened. In conclusion, the Hintz-Ribeiro bridge collapse was mainly caused by severe scour erosion that weakened the bridge foundations. This case study highlights the importance of proper design, regular inspections and maintenance. Understanding factors such as bending moment, stress and beam behavior help engineer improve bridge safety and prevent future failures. Thank you.